as you're aware that we are doing a series on recurrent themes on linear algebra, in which we are discussing some of the themes that have been very much exploited by the TIFR exam, TIFR, NET, GATE, and JEST. Okay, so in that particular series, today we are going to do today we are going to do again an important topic, which is the linear transformations. And let us see uh, how this particular theme has been exploited in recent years. Linear transformations, rotations, reflections. So, although it's not that well exploited, but this is one another important theme that you should be preparing well for your examination. Okay. So first, let us know what is a linear transformation. In our lectures on linear algebra for quantum mechanics, we have already done a good amount of this particular topic. But if you have not gone through all those lectures, and if you directly want to get into what to this particular point, here is a brief outline of the same. So what happens is, let's say if I have a vector space U and if I have a vector space V, if I am making a map such that T alpha U1 plus beta U2 is equals to alpha T U1 plus beta T U2, where U1 and U2 belongs to U and alpha and beta belongs to field F, this particular mapping is called as a linear transformation. In physics, we quite often relate it as linear operators. They mean one and the same thing. Whether you use linear transformation or you use linear operators, they mean one and the same thing. Okay, this is one thing. Now, uh, what you can say is that these particular linear transformations um, have certain sense of some linear transformation are going to indicate some geometrical interpretations. So some of the linear transformation are going to open us some geometrical interpretation that becomes very important in physics. So let us understand some of them. One of them is projection. One of them is projection. So I'm talking about projection transformation. Okay, so let us say that you have a matrix A which is 1 0 0, you have 0 1 0, and then you have 0 0 0. What it is going to do, this particular transformation projects the points in R cube onto R square. Let us see how. So let us say I want to take a vector x1 x2 x3 in R cube, and if I operate this particular matrix, that is 1 0 0 0 1 0 and 0 0 0 over it, what you are going to get, you are going to get x1 x2 and 0. What does it imply? It implies that whatever point was there on your xy, let's say if I'm taking three-dimensional space, it is going to project this particular point, which is, let's say, x1 x2 x3 onto xy plane, because x3 equal to 0 means what? If I'm saying x3 equal to 0, let's say I'm not writing xyz, I'm writing x1 x2 x3. So this particular point, because of this particular a, if I operate, so if I'm doing this, instead of x I'm writing ax, this particular thing is going to project this particular point in R cube on this xy plane, or you can say x1 x2 plane. Instead of xy plane I'm writing x1 x2 plane. Okay, so this is doing what? It is projecting any point in R cube onto R square. Is that clear or not? So this is one of the not even r square. You can say onto uh, in this context I would say onto x on x2 plane precisely. Okay. Now another thing that you can think of is, let's say, shear transformation. Second example that I'm giving you so that you can relate to it is, let us say, shear transformation. Okay. Now you see what is a shearing. So if you know that in small in 11th class you may have understood, you may have read about shear stress. So if I apply a stress here, what it is going to become? This particular let's say square would slightly get enhanced like this way. Okay. So this particular thing can go in the further direction. So this is a kind of shear that you're applying. Okay. So I'll give you a matrix and then you think that whether it gives you a shear or not. So let A be a matrix which I can write it as 1, 3, 0 and 1. And let us define a transformation from r square to r square given by tx is equals to ax. And let us take an example to understand whether it is going to create a shear or not. So let's take an example of a square. Let us take an example of a square which is of, let's say, side um, which is of side 2. So this is how it is. Okay, this is how it is. So what if I apply this kind of, if I do this kind of transformation, that is, if I'm saying that my transformation is this ax, what it is going to do is 1301. Let us apply it on 0 0. It is going to give me 0 0 only. Let us apply this thing on 2 comma 0. It is going to give me 2. If I apply it on 2 comma 0, what am I going to get? I'm going to get 2 comma 0 only. If I apply it on 0 comma 2, what am I going to get? I'm going to get 6 comma 2. And if I apply the same on 2 comma 2, what am I going to get? I'm going to get 8, and this is 6. I think this is 6 and 2, 8 and 2. Okay, so this is what we are getting right now. Okay, so what now I'm going to make, so if I apply this transformation t over this particular square, so what the vertices of the square, what it is happening? So if I apply this t transformation, which is t is given by this particular matrix, t is this 1 3 0 1. If I apply it over uh, the vertices of this particular square, what am I getting? So what am I getting? 0 remains at 0 comma 0 only. This particular thing remains at 2 comma 0 only. No issues about it. This particular coordinate, which is 2 comma 2, goes on to 8 comma 2. So I'm writing it a little bit far. And this particular coordinate, which is 2 comma 0, 0 comma 2, maps to 6 comma 2. So it maps to 6 comma 2. So what will happen? This particular thing will become this way. So it seems that there's a stress applied on the upper portion of the square, and it has gone a little bit further. So this is, you can say that we have applied probably a shear. So that is why I've named it as a shear transformation. Okay, this is one thing. Now you see the same scenario. Uh, Let us say now I'll make a graph a little bit more, you can say, to the scale. So let's say I'll define a transformation t from r square to r square given by tx is equals to 0 minus 1 and 1 0, and let's say I'm applying it on x1 x2. what am I going to get? I'm going to get minus x2 comma x1. This is what I'm going to get, you see. So if your transformation is such that you take an x from R square and the map you are defining is tx, which is nothing but it is equals to multiplying your x1 x2 or operating your x1 x2 by this particular matrix which is given by this. Now we want to see what is the physical implications of the same. So what am I going to do this time? I'm going to make a little bit of graph which will suggest you uh, something, and that's what I want to show you. Let's say I'm making it to quite a little bit of scale. Okay, so let us take some vectors. Let us take some vectors. So let us say this is your 1, this is let's say 2, this is let's say 3, let's say this is 4, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Okay, and similarly I'll do it here also. Minus 1, minus 2, minus 3, minus 4, minus 5, and minus 6. Okay, and see, now I'm going to do something. See, uh, I'll take the point, let's say 1 is origin. Let me take origin. So I know that if I apply 0 0 here, please do remember what is happening. If I take any coordinate x1 x2, and if I apply this matrix over it, that is 0 minus 1 1 0. So after this transformation, this x1 x2 no longer remain x1 x2, and you're getting output as minus x2 and x1. So now just pay a little bit of attention. If I'm marking 0, so 0 comma 0, 0 comma 0 would remain 0 comma 0, right? 0 comma 0 would remain 0 comma 0. Okay, so 0 comma 0 would remain at 0 comma 0. Now if I take a point, let's say 4 comma 2, or use that would be a little bit different. Let's say 4 comma 1. Let us say this point. This 4 comma 1 would be mapped to minus 1 comma 4. So under the transformation, it will be mapped to minus 1 comma 4. Is that clear? If I apply 4 comma 1, if I apply this matrix which is 0 minus 1 1 0 to 4 comma 1, what am I going to get? I'm going to get in return minus 1 comma 4. So minus 1 is this, 4 is this. This is quite clear. Now let us take another point. Let's say it is 2 comma 3. So let's say 2 comma 3. Where 2 comma 3 is going to get mapped to? It is going to get mapped to minus 3 comma 2. I hope it is clear. And let us take the addition of both. So I'm adding 4 comma 1 and I'm adding 2 comma 3. So it will be somewhere here by parallelogram law of vector addition. We know that if this is 1, it is going to get mapped to 6 comma 4. So this is 6 comma 4. So this is the parallelogram, and the image of the parallelogram. So let's say I am doing 0 minus 1 1 0 and I'm putting 6 comma 4 now. What am I going to get? I'm going to get minus 4 comma 6. So that is a little bit difficult. Okay, but let's say it is minus 4 comma somewhere 6 here, or somewhere here, let's say. Now what is happening is a little bit of, okay, so a little bit, I have not made it to scale. So if this is 4, then this is 5, this is 6 somewhere. So what you can see, that this particular parallelogram has shifted by some angle here, and precisely if you find this angle would be 90 degrees. So what has happened, you can say that, and this particular 90 degree you can find, let's say by these coordinates itself. So if you do this thing, let's say, what is this, if you take this and this, and if you want to find, you can take a dot product of both and try to find the cos theta, and then you can find theta is equal to cos inverse. So that is something that you can do on your own, but understand that what this transformation has done, this transformation has transformed the entire parallelogram in a way that it has got rotated by a 90-degree angle counterclockwise. So this particular T has made the parallelogram rotate by 90 degrees in counterclockwise direction. So all these things you should keep in mind. Okay, all these things you should keep in mind. Now another thing that you can think of is reflection. Another thing that you can think of is reflection. So let's say I'm just giving you one example so that you are able to understand what I want to suggest. And then there can be many things in the same category. So if I say, let us say I'm taking a matrix 1, 0 and 0 minus 1. And let's say if I apply it to x1, x2, what am I going to get? I'm going to get x1 as it is, but x2 would be negative of it. So what does it represent? This particular matrix would represent reflection about x-axis. Because if I take a reflection about x-axis of a point x1 comma x2, I am bound to get x1 comma minus x2. Understand, reflection means the distances are same. So this distance remains x2, but this particular point is minus x2 here. Understand? So this particular matrix, that is 1, 0, 0, minus 1, would represent reflection about x-axis. Another thing that you can think is the matrix that I took just before in 2 cross, it was a 2 cross 2 matrix and it represented a rotation. And if you take the determinant of the same, you're getting 1. And if you take the determinant of a reflection matrix, it is minus 1. So one of the important points that for exam you can keep in mind is that reflection matrix, the determinant is always equals to minus of 1. And rotation matrix, the determinant is always equals to plus of 1. This we can also extend to 3 dimensions. So if you have gone through the lecture where I have taught the orthogonal transformations, I have extended this to 3 dimensions also. In 3 dimensions also, you'll find that the reflection matrices will have a determinant minus 1 and rotation matrices will have a determinant plus 1. Okay. Now, because of these linear transformation, as you can see that there are changes in the areas, there are changes in the volumes and things like that. Okay. And if you use the standard basis, then things may be a little bit easier. But if you don't use standard basis, then you'll have to find the area in the transformed, you can say transformed space on your own. Okay, so now what I want to suggest is, just give me a minute. I'll give you one example and then probably you'll be able to understand. Okay, then you will be able to understand what I want to suggest. Just give me a minute. Okay, so what I want to suggest is, let us say that if I have some that I'll show you so that you'll be able to understand them. Just give me a minute. I'll show you what I want to suggest. There was indeed a very good problem that I was looking at. Okay, so I'll take one problem only so that you'll be able to understand what I want to say. So let's say one problem from TFR exam. You just give me a minute. I'll upload that problem and then you'll be able to understand. Okay, which is, I think this is the problem, not this one. So let's say this is the problem. This is a problem from TFR exam. This is a problem from TFR exam. Okay. Now see, understand what it is saying. See, it is saying that consider a set of three-dimensional vectors A, B, and C. And remember, they are not standard basis. They are not standard basis. So what I'm going to do, I'm going to apply this linear transformation that is given to me, and I'm going to see what is the, so what it asks is that these vectors undergo a linear transformation. Matrix M has been given to you, and it says that the volume of the parallelepiped. Do remember, if you don't remember what is the volume of parallelepiped, let's say your vectors are A, B, C, then A dot B cross C. This scalar triple product represents the volume of the parallelepiped. If you remember from your standard 12th, if you don't remember, then please do mark it. So the volume of parallelepiped is given by A dot B cross C. So now what will happen? Having said all these things, I know that one thing is clear to me, that if I'm going to apply linear transformation, obviously this coordinate is going to transform to some space. This particular coordinate is going to transform. This particular coordinate is also going to transform. Now, after having transformed, it is going to create some different a different parallelepiped in the transformed space. Had it been in had it been the ordered basis, then I would have used something called as a matrix of linear transformation, and things are easier there. If you can go back to my lectures, I have discussed all these things in great detail. But here, they are not given in you, or they are not given to you in ordered basis. Okay, so now we'll have to work a little bit. Just let us start with this particular problem. And this has been asked in recent year. I think this is 2022 or 23. I don't know exactly, but I think this is 2023 itself. So let us start with this particular problem. Okay, so if you remember, uh, I'll use this. So I know that my matrix M has been given to me. Now your A gets transformed to A dash. And what is your A dash? A dash would be M times A, and which is equals to 1, 1, 4. You have 1, 0, 1, and this is 2, 1, 1. This is M times A. What is A? A is 1, 0, 0. And what you are going to get out of this is simply 1, 1, and 2. Okay, this is something that you're going to get. Just give me a minute if I don't make a mistake. Okay, so please do remember this is 1, this is 2. Okay, now if I want to see how will B transform, so B under this matrix would transform by MB, it says. So what does it mean? It says that 1, 1, 4, 1, 0, 1, and you have 2, 1, 1. And if I apply B, which is 0, 1, 0, how it is going to get transformed? It is going to be 1, 0, and 1. Okay, and how it is going to, C is going to transform the space. So you see that C now is equal to MC, which is equals to 1, 1, 4, 1, 0, 1, and 2, 1, 1. And now you have applied, I think 1, 1, 2 to it. Now what you're going to get? See, you are going to get something. Oh, I have a lack of space here. So this is 1, 1, 8, which is 10, 1, 0, 1, which is 3 here, 2, 1, 1, this is 5 here, I think. Okay, so this is going to be 3, 10, 3, 5. Okay, so now you see, I'm going to make it for you. So if you remember what was, please do remember your initial coordinates. They were, so if you remember, I'm going to write it here. If you remember that if you have this kind of thing, if this is your A vector, this is your B vector, and let's say this is your C vector, then if I make what you can say a little bit of this, I don't know how to make this. Okay, I'll have to make it to the scale, otherwise you'll not be able to get what I'm trying to say. Just give me a minute. Okay, so so there forms a parallelepiped. Okay, I'll write it here. This is fine. Okay, so let's say this is your A, this is your B, this is your C, and this is what is your parallelepiped. And this volume of this parallelepiped is represented by A dot B cross C. This is represented by A dot B cross C. This is represented by A dot B cross C. Now, or you can say A cross B dot C. So basically what happens is A dot B cross C, you can say that B dot C cross it. So there are six same permutations that you can make out of this. But if I calculate initially what you had, initially the volume of parallelepiped was, okay, initially the volume of parallelepiped would have been found using these vectors, that is 1 0 0 0 1 0 and 1 1 2. But now after having this transformation given by m times A, m times B, m times C, obviously the parallelepiped has, the vertices of the parallelepiped have changed. This has become 1 1 2. So I'll use this thing. So let's say my A is now 1 1 2, B is 1 0 1, and your C happens to be 10 3 and 5. Now if I want to do this, what I'm going to get, let me write A, which is 1 I cap, so I'll write I cap plus J cap plus 2 K cap dot B cross C. So if I write B cross C, then I cap plus 3 J cap plus 5 K cap. I can do it without matrix also here. So I'm not going to waste time in making a matrix here. So this is dot product here. So this is I cap plus J cap plus 2 K cap dot I cross I is simply 0. I cross J is simply K cap. So this is 3 K cap. Then I will have I cross K, which is, if you just remember your childhood days. Okay, if I do I cross K, so I'll get minus J. So minus 5 J cap. I cross, it's K cross I. K cross I is again J cap. So I get 10 J cap. Then K cross J. K cross J is minus I cap. So minus 3 I cap. And then K cross, so so what am I going to get? I hope I'm not making any calculation mistake. Otherwise, this is going to give me a wrong answer. Okay. So again, let me focus. I cross I is 0. I cross J is K cap. I cross J is K cap. So you have got 3 here. Um, I cross K. I cross K is minus J cap. Fine. K cross I is J cap. Fine. And K cross J is again minus. So K cross I is fine. This is fine. So what am I going to get? I'm going to get minus 3 I cap plus 5 J cap plus 3 K cap. And from here, if you just calculate what you're going to get, you're going to get minus 3 plus 5 plus 6. So 3 into 2 is 6. 5 into 1 is minus 3. So you're going to get 11 minus of 3, which is I think equals to 8. So the volume of new parallelepiped, would be 8 units. Would be 8 units. I think answer should be 8 somewhere. Let me see what is an answer. Okay, so answer is 8. So I hope all these things you might have got. Okay, I think you might have got all these things. Now, having said all these things, This is the case of linear transformation. Now, if you are given, if you are given, let us say in ordered basis, then things are little bit easy. But when it is not given in ordered basis, then you have to do in this way only. With regards to rotations and reflections, we are going to take this particular case tomorrow in this lecture series. I hope you're liking this lecture series. In this lecture series, I have already mentioned, I'm going to discuss all those themes which are recurrently being asked in the examination. So right now the theme that I have taken is linear transformation. Tomorrow also we are going to continue with the same, which is the rotations and reflections in linear transformation. I have given you some examples. I'm going to take a few more examples tomorrow. I'm also going to tell you, had it been given in had it been given in ordered basis, then how things would have changed. How things would have changed. This is also something that we are going to see tomorrow. Till then, take care.